Welcome to section 16.2. In this section, we're going to be talking about the concept of line integrals. We're going to see how those relate to vector fields that we talked about last time, how we can evaluate and interpret these results. So this section is definitely the longest section that we have in the entire course. So this one is going to be a bit longer than normal. So everybody buckle up as we're getting through this. We might want to take a break partway through, but let's go ahead and just dive right in. So we're going to define an integral in this section that is similar to a single integral from Calc 1, but instead of integrating over an interval from a to b, we integrate over a curve C. So the concept of a line integral, it's almost a bit of a misnomer because we're not integrating over lines necessarily like we were before. We're integrating over curves. So the way that this works, the way that this is set up, we have a plane curve C given by parametric equations x, y in terms of t. Okay, with t going from a to b, or equivalently by the vector equation r of t is x of ti plus y of tj. And assume that c is a smooth curve, so r prime is continuous and not equal to 0. So here's a diagram to go with this situation. So you can see I have the smooth curve C here. It's just an arbitrary curve. X and Y are written in terms of a parameter T. What we do is we subdivide the parameter so the curve gets cut into n sub-arcs. So think about in Calc 1, right? You take the interval from A to B and we can break it into smaller subintervals and we do like rectangular approximations, stuff like that. We take the ith sub-arc and pick a sample point. So here we have the parameter t. So t is going from A to B. We broke that into smaller pieces. Each of these sections corresponds to one of the sections on the curve. Okay, so we broke the parameter into smaller pieces, and that breaks the curve into smaller pieces. I took an arbitrary section, a sub-arc right here. So we go from ti minus 1 to ti. So that's pi minus 1 to pi. So that's this piece of the curve right there. And we picked a sample point. The sample point is ti star. That gives us pi star, which is xi star, comma yi star. So everything with that star notation just means that that's the sample point that was selected, and it's arbitrary. So this would be how we could compute like approximate values for the integral, just like we do rectangular approximations in Calc 1. But what we're going to do is we're going to take the limit as the sub-arc lengths get smaller for better approximations until we get the exact value. So we're going to shrink these subdivisions smaller and smaller and smaller until we eventually get to the exact value. So notationally, we have f defined on a smooth curve C. The line integral of f along C is given, so it's integral over C of f of xy ds is going to be the limit as the max delta s sub I goes to 0. So s representing like the arc length. So it's the length of each of these pieces. So as the maximum length of each of these pieces is getting smaller and it's dropping to 0, okay, so they're shrinking infinitely, we take the sum with I going from 1 to n of f of xi star yi star delta s sub I. Okay, so we take, right, these are the pieces that are over each of the sections, right? So this is like the length of the curve. This is the height above the curve. So we get that for one section, add it up to the next section, to the next, the next, for all of the sections. And then by taking the limit, those approximate areas give us the exact. Okay, eventually it shrinks down enough that we get the exact value. Recall, the length of a curve is given using an integral. So this is the integral from a to b of the square root of dx dt squared plus dy dt squared dt. This is the general formula for arc length for parametric equations, parametric curves. So these two pieces of information together will give us a formula to calculate line integrals. So we say the line integral of f of xy ds over c is the integral from a to b of f of x of t, y of t, times the square root of dx dt squared plus dy dt squared dt. So everything here is in terms of t. Okay? All the x's, the y's, the derivatives, everything is in terms of t, and it's getting evaluated from a to b. So another way to think about this formula, if we think about this in terms of like the general arc length formula, if s of t is the length of the curve between RA and RT, then the derivative of s with respect to t, so remember, like s of t is that length, the derivative is that arc length formula, so the square root dx dt squared plus dy dt squared. Which, if we use differentials, just multiply that across over there. So we get ds is the square root of dx dt squared plus dy dt squared dt. So all this is basically saying is, if we go back to this formula up here, the ds is getting replaced by this because of that arc length relationship. So again, ds is just getting replaced by this in that formula. And again, we want to express everything in terms of the parameter t. So everything is getting put in terms of that parameter. Now with line integrals, we can evaluate them over any general curve, but if we look specifically at the case where the curve is a line segment from A0 to B0, we use x as the parameter, and we get the following. X is itself, y is 0, because that's where we are along the x-axis here. X goes from A to B. The line integral becomes the integral from A to B of f of x comma 0. And the derivative of x would be 1. Derivative of y would be nothing. So that just becomes 1 dx, because we're saying x is the parameter. And this formula is just a single integral from Calc 1, right? Single variable, single integral from a to b of f of x dx. So it turns out that the single integral from Calculus 1 and 2 actually is a special case of the line integral from Calc 3. Now, obviously, you need so much information to be able to put it into that context, which is why we don't teach it that way. But now we have a bigger picture, and we can see that those single integrals are just cases of line integrals being evaluated over the x-axis. Just like normal single integrals, we can interpret the line integral of a positive function as an area. So you can see down here I've got a visualization. I've got a little bit of a graph here. So you can see the curve C is down here in red on the bottom in the XY plane. And then the surface is the orange part up here. So the surface continues in all directions here. But we are finding the value between the surface and the curve. So if f of xy is greater than or equal to 0, the line integral over C represents the area of one side of the fence here. So you can see like it builds like this fence sticking up, right, into 3D. So if we take one side of this fence all the way along, that's going to give us an area. That area is what the line integral gives us. So the line integral is giving us the area of one side of this fence sticking up above the curve C, below the function f. Okay, so we have our surface up here. Okay, so we're going under the surface but above the curve specifically. Okay. So let's take a look at an example. So evaluate line integral over C of 2 plus x squared y ds, where C is the upper half of the unit circle, x squared plus y squared equals 1. So if we look at the upper half of the unit circle, something like that. So we're evaluating, so this is our curve C. So x squared plus y squared equals 1. So that's going to be 1, and that's going to be negative 1 over there. That's the origin right there. We only want the top half, right? So that would be y greater than or equal to 0. What we want to do is we want to come up with a parameter. We want to parameterize this. So we need to think back to our parametric equations. When we're working with circles, we can go ahead and use like things like polar. But we get the parametric equations for the unit circle. We're going to have x equals cosine of t, y equals sine of t. And because we're only working with the upper half of the unit circle, t is just going to go from 0 to pi, not 0 to 2 pi. So again, that's just because we're dealing with the upper half. So this is how we parameterize the unit circle. And we need to remember that. That's going to be one we'll use quite a lot. So the line integral over C of 2 plus x squared y ds is going to be the integral from 0 to pi of 2 plus x gets replaced with cosine of t, so that's cosine squared t, y is sine of t, times the square root of derivative of x with respect to t squared. So that would be, so dx dt is going to be negative sine of t. dy dt is going to be cosine of t. So if we square this, it becomes positive. So we get sine squared t plus cosine squared t dt. This here, this object here, sine squared plus cosine squared equals 1. The square root of 1 equals 1. So that term essentially just disappears because it's just being multiplied by 1. So we're left with the integral from 0 to pi of 2 plus cosine squared t times sine of t dt, which gives us 2t, and then you can do like a u substitution, right, or a trig sub. For this one, we get minus cosine cubed t over 3, and all of this is evaluated from 0 to pi, which when we do that, we end up getting 2 pi plus 2/3 for the exact value of that line integral. So we have a surface 2 plus x squared y that we are finding the area beneath, but only the area that lies above this half circle here. Okay, and that area is 2 pi plus 2/3. Now, we have plenty of cases of curves that are not quite as simple as that. So suppose that C is a piecewise smooth curve. So you can see I've got, right, a bunch of different pieces of curves here that are all connected. In the case where we have multiple pieces of a curve, we can still evaluate the line integral. We just have to evaluate it over the different pieces separately. So we're going to get, if we have like C1 through like Cn, whatever, we would get the line integral over C1 of f of xy ds plus the line integral over C2 of f of xy ds, etc., all the way up through Cn, so whatever the top or the last curve is. So if we want to evaluate a line integral over a piecewise curve, we can. We just have to evaluate the pieces separately. Let's take a look at an example with this. Evaluate the line integral over C of 2x ds, where C consists of the arc C1 of the parabola y equals x squared from 0, 0 to 1, 1, followed by the vertical line segment C2 from 1, 1 to 1, 2. And you can see I already have a graph over here set up. So that's C1 and that's C2. So we need to split these up. So we'll work on C1 first. Now, the nice thing about when we have a function like this, so we have y equals x squared, we always are trying to come up with what the parameter should be, that we can write everything in terms of that one parameter. When the function is set up like this, like y equals a function of x, we don't have to create a parameter t. We can just use x as the parameter, because x will be itself, and then y can be written in terms of x. So it's just the same as if we had called it t, and then just rewritten it in terms of that. So we can say since C1 is a function, y equals x squared, use x as the parameter. So C1, we get x equals x, y equals x squared, and x is going from 0 to 1. So the line integral over C1 of 2x ds will be the integral from 0 to 1 of 2x, and we don't have to convert that because it's already in terms of x, times the square root of dx, which is 1 squared, plus dy dx, so that's 2x squared, so that's 4x squared dx. You can set this one up using a substitution as well. We end up with 1/4 times 2/3 times 1 plus 4x squared all to the 3/2 evaluated from 0 to 1. So not a particularly pleasant outcome for this one. We end up getting 5√5 minus 1 all over 6. So this is, this is the value of the line integral over C1. So over this parabolic curve. Then for C2, we have a vertical line segment. So that is just x equals 1 is the equation there. So x will always be constant. It'll always be 1. Y can be anything, right? Y can just be itself. So we'll go ahead and choose y as the parameter. So C2, we get x is 1, y is y, right? Y is itself. And y starts here and goes up to here, right? Or here to here, so that's 1 to 2. So y goes from 1 to 2. So the line integral over C2 of 2x ds, we get integral from 1 to 2. X is 1, so that's 2 times 1, times the square root of dx dy, so that's nothing, plus dy dy, which is 1, dy. So we have integral from 1 to 2 of 2 dy. So that's just 2y evaluated from 1 to 2, which is 2. So that would be the value of the line integral over C2, over the second part of that curve. Thus, the line integral over C of 2x ds, so the line integral over the entire thing, is just the value over the first curve plus the value over the second curve. So we just add those two together. And that's going to give us our total for the entire curve. Okay. Now we can also evaluate, integrate with respect to x and y. It doesn't just have to be ds, like with respect to arc length, like we've seen. So we can also integrate with respect to x and y, evaluating by expressing everything in terms of t. Okay, so dx would be x prime of t dt, dy would be y prime of t dt. If that's the case, then the line integral over c with respect to x is the integral from a to b, f of x of t, y of t, times x prime of t dt. And then same idea with respect to y, f of x of t, y of t, times y prime of t dt. So essentially x prime and y prime are taking the place of like what s prime was, so that arc length formula, okay, when we integrate with respect to x and y instead of s. We will often have a case where we evaluate line integrals with respect to x and y together. So instead of writing them as their own separate integrals, we end up just writing this as the line integral over c of p of xy dx plus q of xy dy, like that. So we end up eliminating one of the integral symbols. This is just a shorthand. They're still being evaluated. individually, but everything in both of these is going to get put in terms of t. Once it's all in terms of t, this can all just be one integral anyways. So this is just a faster way of doing that. A note at the top of the next page here. So one of the most difficult aspects of setting up a line integral is determining a parametric representation for a curve. So a lot of times if we can use x or y as the parameter, we like to do that because that's the most straightforward, especially if you have a function. But, we've seen things where we parameterize circles with like cosine and sine, with like polar coordinates. And we've seen some other examples as well. One of them that we talked about a long time ago in the first chapter of this course that I mentioned at the time we would need later. Well, it's later. And so we need it now. The vector representation of a line segment that starts at R0 and ends at R1 is given by R of t equals 1 minus t times R0 plus t times R1, with t going from 0 to 1. Now, this formula for parameterizing a line segment and like writing it as a vector function, this is not the only way to come up with a parametric representation for a line. This is not the only way to do it. There are other ways. Lines are functions, right? So you can find the equation of the line and use that as the parameterization. But this one is nice and unique because of this. Because t is going from 0 to 1, if we use this parameterization, t will always go from 0 to 1, no matter where the line begins and ends. So we like this version of the formula for the sake of consistency. The parameter t will always go from 0 to 1 if we use this version of the linear formula. Okay. So we're going to see this one pop up a lot. We work with lots of linear functions at this level. So let's take a look at this example here. Evaluate the line integral over c of y squared dx plus x dy, where c is c1, so that's the line segment from -5, -3 to 0, 2. And then separately for c2, which is the arc of that parabola, x equals 4 minus y squared, between the same 2 points. So I have the two cases drawn out here, but these are two separate parts, so we're not looking at combining them in any way. So we're going to evaluate the line integral over c1, and then evaluate the line integral over c2, and see what we get. All right, so part A. This is a line segment. So for our parametric representation for the line segment, we're going to have R0 is -5, -3, and R1, that's the ending point, that's 0, 2. So for R of t, we get 1 minus t times -5, -3, plus t times 0, 2. So that's -5 plus 5t, and -3 plus 3t, plus 0, 2t. So we get -5 plus 5t, and combine those two, we get -3 plus 5t. And that's going to give us x and y. So we get x is -5 plus 5t, y is -3 plus 5t, and t goes from 0 to 1. Again, because of that parameterization, it always will go between 0 and 1. And that's nice because then it doesn't matter where the line started and stopped. parameterization has the same bounds. We also will need dx and dy. So derivative of this is 5, so that's 5 dt. dy is also 5 dt. So line integral over c1 of y squared dx plus x dy is integral from 0 to 1. Everything gets put in terms of t. So that is -3 plus 5t quantity squared dx. So that's times 5 dt plus x. So -5 plus 5t dy. So times 5 dt. If we simplify this down, so there's a common factor of 5 in both of those. I'll go ahead and pull that out to the front here. Foil this out, combine like terms, we get a 25t squared minus 25t plus 4, and that's all dt, so with respect to t. This one is just single integral, single variable, so I'll just tell you we get -5 over 6 for that one. So the value of the line integral is -5 over 6 over c1. So if we're thinking of this in terms of area, clearly this function is not positive over that entire interval, so it dips below the xy plane, so we are getting some negative values out of that, and that's okay. So we're still able to evaluate it as normal. For the second part, let me change up my color here. So for part B, we have the arc of a parabola, x equals 4 minus y squared. So this one, because it's given in this functional form with x in terms of y, we can go ahead and use y as the parameter. So since it's a function of y, use y as the parameter. So if we're ever given functions like this, we might as well use them to our advantage. So we get x is 4 minus y squared, y is itself, and y is going from -3 to 2. So our line integral over c2 of y squared dx plus x dy, let's see. Oh, we're going to need dx and dy. So dx is going to be -2y dy, and dy is going to be 1 dy. So it's just itself. All right, so we get integral from -3 to 2 of y squared times dx, so that's going to be times -2y dy, plus x, so that's 4 minus y squared, dy, which is just itself. So integral -3 to 2. If we combine like terms, we end up getting, actually I don't think there are any like terms in this. We just get -2y cubed minus y squared plus 4 dy. Single variable, single integral, so I'll just tell you we get 245 over 6. Is the value of the line integral over c2. So I want to draw our attention, and this is the little blurb down here. Notice in this example, we got two different values, even though we had the same endpoints, right? So we started and ended at the same place, but we took two different paths, two different approaches to get there. Okay? In general, the value of the line integral depends not just on the endpoints, but on the path. Okay? This is the path that we take to get there. Okay? Because the function will behave differently over these two curves. So we should, in general, be getting different answers. Now, in the next section, we will be looking at exceptions to this rule. So we'll see cases where this may not happen. But again, that will be for a different discussion. Notice if negative C1 here, or read more as like the opposite of C1, denotes the line segment from 0, 2 to negative 5, negative 3. So if we took the same line segment but went backwards, we would get x equals negative 5t, y equals 2 minus 5t, t would still go from 0 to 1, and the integral over the opposite of c1 of y squared dx plus x dy would actually give us 5 over 6. So compare that to the value we got up here. It turns out that the direction or the orientation of the curve matters when it comes to evaluating the line integral. So evaluating the line integral over the line from negative 5, negative 3 to 0, 2 gives us exactly the opposite value as evaluating it from 0, 2 to negative 5, negative 3. Okay, so the direction we're going on the line matters. That's why I have these little arrows up here pointing our direction out, because we will get different answers depending on which direction we go. Right. Up here, top of the next page. In general, a given parameterization, so x of t, y of t from a to b, determines the orientation of a curve C with positive direction corresponding to increasing values of the parameter t. So basically, as t counts up from a to b, that will give us the positive direction of the curve, okay, the positive orientation. So if the opposite of C here, the negative C, denotes the same curve with opposite orientation, then the line integral over the opposite of C of f of xy dx is negative line integral over C of f of xy dx. Same thing here with respect to y, we get the opposite of the line integral over C. And this is because x and y are both directional, right? X has a positive direction and a negative direction. Y has a positive direction and a negative direction. So if you're going the opposite direction, you're going to get the opposite answer. But if we integrate with respect to arc length, the value of the line integral does not change. So the line integral over opposite of C is equal to the line integral over C with respect to S, with respect to arc length. So again, delta x and delta y change sign when we reverse the orientation, but arc length, the curve will be the same length whether you go forwards or backwards. So arc length is always positive along these curves. This is why we like to use arc length when possible, because we are able to evaluate it without consideration of orientation. So we can evaluate it. It'll be the same either direction, whereas x and y are not. As with everything that we do in here, we can take the concepts we see in 2D and bring them up into 3D. So now we have C as a smooth space curve with parametric equations x of t, y of t, z of t. The line integral with respect to arc length, so ds, is the integral from a to b of f of x of t, y of t, z of t times the arc length formula, shifted up into 3D. So we have square root of dx dt squared plus dy dt squared plus dz dt squared dt. But we can also create a little bit more of a compact notation, so we don't have to write that square root out every single time, because we have seen arc length before with respect to vector functions. So if we consider this x, y, and z as components of a vector function, we can rewrite this as integral from a to b of f of r of t times the length of r prime of t dt. So this version of the formula is pretty frequently used because it condenses all of this. So r of t is just a vector function whose components are x, y, and z, all in terms of t. And then the square root of the sum of the components squared. This is a magnitude formula, and the components are derivatives. So that's the length of r prime. Okay, so this is how we can find the value of a line integral in space. Notice also when the function itself that we're integrating is 1, we get line integral over line integral over c of 1 ds. So that integrand, that function was just 1, so it's just magnitude of r prime of t dt. And that was the formula that we had for arc length. So that would be arc length. So if we evaluate the line integral over c of the function 1, right, it always kind of takes us a step down. Instead of finding an area, we find a length. So line integrals with respect to x, y, and z can also be defined here. So we have integrals of the form, so p dx plus q dy plus r dz. So just like the others, except, of course, with 3 components instead of 2. Let's take a look at some more examples. Evaluate line integral over c of y sine of z ds, where c is the circular helix given by these equations. So we have worked with this circular helix before back in our first chapter. But they've already given us the parameterizations, and that's really the hard part of these problems. So once it's all parameterized, we can just substitute in. So t goes from 0 to 2 pi. Y is sine of t. Sine of z is just t. So sine of t times sine of t times the square root of derivative of x is negative sine squared is just sine squared plus derivative of sine is cosine squared plus derivative of t is 1 squared is just 1 dt, like that. So these two give us a sine squared of t. Sine squared plus cosine squared is 1. 1 plus 1 is 2. So we can just, actually, I'll just put this out in front here. That'll be a radical 2. Integral of sine squared of t dt. We need to use like trig identities, trig properties to solve that, but I'll just cut to the chase here. The integral itself gives us pi, so we end up with pi times radical 2. That would be the value of the line integral. So it's nice when they give us the parameterization to begin with. If we take a look at this next example, evaluate the line integral over c of y dx plus z dy plus x dz. So we're kind of just jumbling the components around a little bit, where c consists of the line segment from 2, 0, 0 to 3, 4, 5, followed by the vertical line segment c2 from 3, 4, 5 to 3, 4, 0. So for c1, so this is a piecewise, right? We've got two separate line segments that are connected together. So we need to parameterize them separately and evaluate them separately and just add them together. So for the parameterization of this line segment, so recall, r of t equals 1 minus t times r naught plus t times r1. Okay, so we end up getting, I'll spare you the work on this, but plug in the starting point and the ending point. We end up getting x is 2 plus t, y is 4t, and z is 5t, and t will go from 0 to 1. So, line integral over c1 of y dx plus z dy plus x dz is integral from 0 to 1. Y is 4t. dx, so that's the derivative of x, is just 1 dt. Plus z is 5t. dy, derivative of y is 4 dt. Plus x, so that's 2 plus t. Times dz, so that's derivative of that is 5 dt. So everything's in terms of t now, so we don't need 3 of these. We'll just put 1 in the back. But we get 4t and 20t and 5t. So that's going to be 29t plus 10 dt, which ends up giving us 49 over 2. Or if you prefer decimals, 24.5. So that would be C1. C2, the vertical line segment, we can parameterize in the same way. Or you could just work with, like y as, or excuse me, with z as the parameter, right? Because x is 3, y is 4, z changes from 5 to 0. So you can absolutely find a way of setting that up. But just for consistency's sake, if we parameterize using the same formula, the same way, we end up still getting x is 3 and y is 4. And we end up getting z is 5 minus 5t, with t going from 0 to 1. So again, the key here to this formula is consistency. We can parameterize this in a different way if we want to, but if we use this formula, t will always go from 0 to 1. So we like the consistency of that. Notice here that dx, because that's a constant, is going to be 0, and dy will also be 0. Dz is going to be negative 5 dt. But we end up with the line integral over c2 of y dx plus z dy plus x dz. The dx term and the dy term become zeros, so they're gone. All that's left is x, so 3 dz, so negative 5 dt, from 0 to 1. So we get integral from 0 to 1 of negative 15 dt, which is just negative 15. So line integral over c over the piecewise smooth lines here is just the sum of these two. So 49 over 2 plus negative 15, which works out to 19 over 2. Or again, 9.5 if you like decimals better. So, but we end up with that value for our line integral. Now, one of the things that we can do with line integrals, because we haven't really talked about section 1 yet in the concept of vector fields, we can evaluate line integrals of vector fields. So let f be a continuous vector field defined on a smooth curve C given by a vector function r of t, with t going from a to b. Then the line integral of f along C can be written in a few different ways. So we have line integral over C of f dot dr, and that is a dot, not a times, because we're dealing with vectors here. And then this r is supposed to be a vector. So we get the integral from a to b. This is f of r of t dotted with r prime of t dt. And we can also see it occasionally written line integral over c of f dotted with capital T, that's the unit tangent vector, ds. But the main version of this formula that we're going to use is this one. Okay, so that's f of r of t dotted with r prime of t dt. So all this means, r of t, remember, is just the x, the y, and the z, all in terms of t. So f of r of t is just f of x of t, y of t, z of t. So we're just plugging everything in terms of t. And dr becomes the r prime of t dt. So pretty similar setup to the ones that we've looked at so far, just with vector fields instead of scalar fields. This integral of the vector field gives us the concept of work. Not just that it gives us work to do, but the physical, like the physics and engineering concept of work. So work performed by a force in moving like an object, for example. So like in this problem, it says find the work done by the force field x squared I minus xyj in moving a particle along the quarter circle r of t, cosine of ti plus sine of tj. So this is like the unit circle, but only a quarter of it. So 0 to pi over 2. So what we have here, we have x is cosine of t, y is sine of t. So f of r of t, all that means is replace the x's with cosine t, replace the y's with sine of t. So we get cosine squared t I minus cosine t sine t j. Okay. And then r prime is just the derivative of this. All right, so r prime of t is negative sine of t I plus cosine of tj. So to evaluate for the work done, we're going to take the line integral over c of f dot dr. So that's the integral from 0 to pi over 2 of f of r of t. So that's this first one. So that's cosine squared t and negative cosine t sine t dotted with r prime of t. So that's negative sine t and cosine t dt. So if we evaluate that dot product, we get negative cosine squared t sine t, and then we end up getting minus cosine squared t sine t dt. So we end up just getting kind of negative 2 copies of the same thing. So 0 to pi over 2, negative 2 cosine squared t sine t dt, which again you can set up using like a substitution, and I will tell you we end up getting negative 2/3 for this. Now, the natural question typically is, how would we get out a negative value for work? Isn't work being done like a positive quantity? Well, because we're dealing with vectors here, direction is also very important. So we're not saying that the work being done is negative. We're saying that the amount of work it would take for the vector field to move the particle in that direction is negative because it's going the wrong way. So I have a picture down here. Here's the vector field that we're working with. Okay, so this is all F. These are all different vectors from F. And then here's the quarter circle. And we're going from 0 to pi over 2. So we're heading counterclockwise, right? We're heading to the left here. But the vector field is pointed to the right. So the reason that we get a negative value for work is because if the vector field was going to be able to push the particle to the left, it would have to turn around. It would have to be negative in order to go backwards and push the particle that way. If we were going forwards, so like if we were going clockwise, if we were going this way, the vector field would be pushing with that direction, so we would get a positive number here. And remember, if we take the curve in the opposite direction, right, opposite orientation, we get the opposite value. So we would end up getting positive 2/3 here instead of negative 2/3, right? And that note is actually at the top of the next page here. The line integral over opposite of c of the vector field is equal to the opposite of the original line integral. The reason this happens with vector fields in particular is because of the tangent vectors. Because like the tangent vector, if we're going that direction, points that way. But if we're going the other direction, it points that way. Okay, so direction and orientation are very important when it comes to evaluating line integrals, especially with vector fields. So let's take a look at another example. So evaluate line integral over c of f dot dr, where the vector field in question is xyi plus yzj plus zxk, and c is the twisted cubic given by x equals t, y is t squared, z is t cubed, from 0 to 1. So we've worked with the twisted cubic a little bit before, like way back at the beginning of the semester. But we just need to assemble the pieces here that we need in order to calculate the line integral. So r of t is just going to be t squared, and t cubed, right? That's the x component, the y component, the z component, all in terms of t. R prime of t is going to be 1, 2t, and 3t squared. And f of r of t, so we take this vector field up here and substitute in these values. So we get x times y is going to be t times t squared. So that's t cubed. Y times z, so this one, is going to be t squared times t cubed. So t to the 5th. And z times x, that's t cubed times t. That's t to the 4th. So, for our line integral over c of f dot dr, we get integral from 0 to 1 of f of r of t dotted with r prime of t dt. So that's integral from 0 to 1 of t cubed, t fifth, t to the fourth, dotted with 1, 2t, and 3t squared dt. So we get t cubed plus 2t to the sixth plus 3t to the sixth dt, which you can combine those to make 5t to the sixth. And then you just got single integral, single variable. I'll just tell you, we end up getting 27 over 28 for this. So almost 1. That would be the value of the line integral over the vector field. Now, to draw just a little bit of connection here between the two, so there's some stuff that's already pre-set up down here. If we take the line integral of the vector field f dot dr, so we have the formula for it right here. If we rewrite these in terms of their scalar function components, so this one would be pi, qj, and rk. R prime would be x prime, y prime, z prime. If we dot these together, so p goes with x prime, q goes with y prime, r goes with z prime, we get this formula, which of course is not that nice to look at, but if we just kind of ignore all of the inner components here, we get p times x prime of t dt, q y prime of t dt, and r z prime of t dt. So if we write it in the shorthand, we get line integral over c of p dx plus q dy plus r dz. And that was, so that's this right here. That was the formula we found working with scalar functions, p, q, and r, back earlier in the section. So basically what this is showing us, what this is doing for us, is it's drawing a direct connection between the evaluation of a line integral of a vector field and the evaluation of a line integral with a scalar field. So this is a direct connection between the two. So like, for example, we had a previous example where we evaluated y dx plus z dy plus x dz just a little while ago. So this could be written as line integral over c of f dot dr with the vector field of xyz just being y, z, and x. So if we had set up this type of line integral of the vector field and that was our vector field, we would get exactly this, which we have already evaluated without vector fields. So again, there is a definitive connection between line integrals of scalar fields and line integrals of vector fields that we can define. But that brings us to the end of the section, our introduction to line integrals. You can see already that we're using a lot of properties from throughout the course, and it's just going to get more so as we're going through. So never a bad time to go back and review some of our past material, because we're going to be using all of it. When we return in the next section, we're going to look at another way of evaluating line integrals, and see how the concept of a conservative vector field comes back into play from the first section. We're going to take look at that next time.